All right, in this video, we're going to tackle the proof of the chain rule. It's not that big of a deal, but I figured I would just separate it from the other stuff so that we could really focus on using it and understanding the intuition separately. Remember, this is what we discovered at the end of the last video, that we have this multiplication of rates of change linking things together. And this is the visual that we were thinking of, right? We had these gears that were turning, and as they're turning, they're impacting the rate of change of the gear next to it. And really, it's the size of the gears doing this, right? This is just a physical phenomena that we've probably seen before in transmissions or on bicycles, things like that. But we can multiply these rates of change across gear to gear to get the connection between gear A and C. So we can use this B gear as kind of a linking rate of change, hence the chain rule here, to connect these things. Hopefully the intuition is there. All right, so let's see the actual proof of this chain rule. Remember, what we're looking at is to differentiate this composed function and see that this is really the product of these rates of change, dy over du times du over dx. In our proof, we're going to be looking at it this way. We're going to be looking at the derivative of f of g of x, and we're going to notice that that's the derivative of f evaluated at g of x times the derivative of g at x. Okay, so here we go. First, we're going to say let y equals f of u be differentiable at u, and u equals g of x be differentiable at x. That's our standard setup that we have already. And now notice that y is really equal to f of g of x through this nice change of variables that we have. So if we want to find dy over dx, that's really the derivative of this composition of functions. And here it is by the limit definition. Normally we have f of x plus h, right? But now we have this f of g. We're still going to evaluate at x plus h. So the x plus h part still goes right in here. All right, so there's our limit of f of g of x plus h minus f of g of x all over h. And then what we're going to do is multiply by 1. We've seen this trick before, right? In the proof of the product rule, we use a similar trick. We're going to pull this g of x plus h minus g of x over g of x plus h minus g of x out of a hat and say this is going to be useful to multiply by. Why is that going to be useful to multiply by? Well, let's show you. There's a really nice property that we're going to use here. When you multiply fractions, the way that we multiply fractions, let's just do a silly example, is that we multiply the tops and we multiply the bottoms. The numerators get multiplied together and the denominators get multiplied together. But we know that multiplication is commutative. Normally we'd think that that means that switching the order of the fractions is fine. But what that also means that if we just look at the product in top or in the bottom, we can switch the order there. So this is the same thing as 3 times 2 over 7 times 4, which we could write as 3/7 times 2 over 4. Or we could say this is 2 times 3 over 4 times 7. Same thing. 2/4 times 3/7. So notice we can just shuffle up numerators and denominators here pretty easily as well. We're going to do that right here. What we're going to do is take this g of x plus h minus g of x and this h, and we're going to swap them. So here we go. We've got all of this stuff here. But now we'll notice it's the exact same thing, but we're swapping the denominators. Also, I had a limit of a product. I'm going to split that up into a product of 2 limits. We should recognize this. Doesn't this kind of look like the limit definition of the derivative of g of x? That's good. We wanted that, right? And now what we want is that we hope this thing can get turned into f prime of g of x. So we're going to see kind of another limit definition here, but we're going to need to do a little bit of work to get it. All right, so in order to do that first limit, we're going to use another change of variables. Oh my goodness, so many changes of variables. We're going to look at t equals g of x plus h. So we're going to call this thing here t, and this thing here t. And then we're going to say g of x is u, so that's going to be u, and that's going to be u. So we'll really have f of t minus f of u over t minus u, and then we have to figure out how this limit as h goes to 0 is going to work. So notice that when h goes to 0, g of x plus h we can say that's like it goes to g of x plus 0. We know that because we have continuity of g because we had differentiability of g. And we know that as long as g is differentiable, it has to be continuous at that point. So that's going to work out nicely, meaning as h goes to 0, t is going to approach u. That's pretty cool. So then, since f is continuous at g of x, because again, we said f was differentiable at g of x, or at u here, then we have that as h goes to 0, f of t approaches f of u, because again, this thing here approaches g of x plus 0, and so that approaches g of x, and so we get this nice f of u. All that to say, like we said earlier, f of t minus f of u over t minus u, limit as t approaches u. Maybe we recognize this too. We normally had like x approaches a, right? Of f of x minus f of a over x minus a. This is the limit definition of f prime at u. So we have g prime of x and f prime of u here. Well, that's good news because remember what u was. Again, f prime of u times g prime of x, but u was equal to g of x. So we have f prime of g of x times g prime of x. That's the chain rule as expected. End of proof. Real short video here. Again, that's the proof of the chain rule using the limit definition. This is going to act as our intuition, this kind of idea of multiplication of rates of change to get from one gear to the next. Hopefully that's helpful to see what's going on. In our next video, we're going to focus on actually using this chain rule. So we're going to have to focus on identifying these inside pieces here and figuring out how to differentiate the outside piece with regard to u, right? dy over du times this derivative of the inside piece, du over dx. So that'll be a bit of a challenge to get used to actually working with the chain rule, but for now, hopefully we're happy with the proof of this thing.